Okay, so this is going to be a half tablet talk, which will require me to be able to synchronize my tablet. There we go. Okay. Thanks so much, Susie, for the introduction. And well, thank you very much to the organizers for inviting me. That's like really nice to be here. And it was also really great to be able to hear about so many topics in the past 2 days. So it's nice to have a conference that deals with a lot of different things. All right, so what I'm going to be talking about today is TT-bar deformations, and more specifically, TT-bar deformations in curved space from four-dimensional Chern-Simons theory. I'm going to follow a very intuitive structure for this talk. Essentially, I'm going to define the first big word first, TT-bar deformations. And I think I'm going to spend like most of the talk, maybe 2/3 or 3/4 of the talk actually talking about that because of the motivational and background aspect of this conference. Then I'm going to define the second big word, which is four-dimensional Chern-Simons theories, and explain in principle how we can extend like 3D Chern-Simons theory to 4D Chern-Simons theory. And then if time permits, I'm going to talk about the actual results. Like this talk is based on a paper that I wrote approximately like a year ago. And really the only thing that would be my contribution to this would be the very last part, which we're probably going to spend like 3 or 4 minutes on. But which is going to explain how we can use this four-dimensional Chern-Simons formalism, insert surface defects in there, and after shaking it real hard, get to a two-dimensional theory that is TT-bar deformed. All right, so without further ado, let's start talking a bit about TT-bar deformations themselves. These deformations were introduced by like simultaneously, like independently by Zamolodchikov and Smirnov, and by another group, Cavaglia, Negro, Tateo, and Cecchini, a few years ago, I believe like around 2016, 2017. And they can be rather simply defined as being a flow in the space of two-dimensional quantum field theories. So for this talk, we're going to focus only on 2 dimensions. We're going to talk only about two-dimensional quantum field theories. And let me give now the definition. If you consider a trajectory in the space of two-dimensional quantum field theories, a trajectory that is going to be parameterized by what I'm going to call a deformation parameter lambda, that's going to range from 0, which is corresponding to the non-deformed theory, to plus or minus infinity, depending on which sign you choose, which is going to correspond to very largely deformed theory. Then at each point of this trajectory, you will have a QFT standing with deformation parameter lambda. And this QFT is going to have a stressed answer that I'm going to call Tij or T mu nu upper script lambda, and a Lagrangian L lambda. Now, in order to get a TT bar flow, what we want is the following differential equation. We want that the evolution of the Lagrangian of the theories along this flow, so del lambda L lambda, we want this to be plus or minus. I'm saying plus or minus, it's just a matter of conventions. You can choose plus, you can choose minus. I think I'm going to choose plus for most of it. But, the determinant of the stressed answer of the already lambda deformed theory. Meaning that if you are positioning yourself at one point of this trajectory, this corresponds to an already lambda deformed theory. If you want to deform it further, then you deform the Lagrangian by the determinant of the stressed answer at that point. In other words, the Lagrangian at lambda plus delta lambda is just going to be the Lagrangian at lambda plus delta lambda, or plus or minus, if I want to continue saying plus or minus, delta lambda times determinant of Tij lambda. So this is going to define, this is the definition of TT bar deformations. And it's defining a flow in the space of QFTs that essentially progresses from a seed QFT at lambda equals 0, which is going to correspond to an infrared theory, and is going to flow towards the UV to a theory at lambda different from 0. Now, if we want to be a little bit more precise as to what the deformation looks like, because we're working in 2 dimensions, we can always do this little change of variable between x, y, and like complex coordinates. And then our determinant is going to look like t z z, t z bar minus t z bar squared. And this is where we kind of want to get, well, understand why this is called TT bar deformation. This we can just call t. It's the holomorphic part of the stress tensor. This we can call t bar, anti-holomorphic part, and this we can call theta, and this is the annoying part that makes it an abusive language of saying TT bar deformation, because usually people are still going to call this operator TT bar. But the main point is, what you're really going to have, if you want to rewrite the flow equation, it's del lambda L lambda is going to be TT bar at lambda, all of them, minus theta at lambda squared. That's for all QFTs in 2 dimensions, and these deformations are defined for all QFTs in 2 dimensions. Now, if you take the specific example of a conformal field theory, then your TZZ bar is going to be 0, and then you get the actual like TT bar deformation per se. In this talk, we are going to be interested in conformal field theories. So this is the only form that will matter to us, but the deformations are a little more general than this form. Now, what we are going to work on is infinitesimal TT bar deformations. So we're not going to consider an arbitrarily large deformation. Instead, we're just going to consider the deformation parameter lambda to be arbitrarily small. And in this limit, then we can write that L lambda is just L0 plus lambda times the determinant of Tij, 0, which is just L0 plus lambda TT bar. This box is stupidly small. And this is the form that we are going to use at the end of the talk for the results section. Now, this is all nice and well. We have a deformation that is pretty well defined. However, the bad omen in all this is that this deformation is irrelevant. It flows from the infrared to the ultraviolet. And an irrelevant deformation in physics is never really a good sign, because it means that according to like general arguments of renormalization, it will require an infinite amount of counter terms in the Lagrangian to make sense of the theory and to actually compute physical quantities. So in practice, it seems like an impossible to use kind of deformation. Now, how do we get out of this? Well, it's not that we really do get out of this, it's that these TT bar deformations are going to have an extra property, which makes them very nice, which is that they are actually solvable. What does that mean? It means that in spite of the fact that they seem hard to deal with, actually, if we have the data of the seed QFT, then from that data alone, we can deduce explicit and exact quantities for the deformed quantum field theory. And this alone makes it worth studying because, well, again, if we know the initial theory, we know everything about the final theory, the deformed theory. In particular, we can get lots of very relevant physical quantities. Yes.
Oh, thank you. So I want to ask you this. So you start with a seed QFT,
Yes.
and you can compute things there. So you know stuff regarding
Yes.
that QFT, like
Yes.
correlators and so forth.
Yes.
Could I think of this deformation as some sort of like a Taylor expansion in the deformation parameter and just taking it to be linear at the linear level because of assuming it being too small, small enough or something like that?
Infinitesimally, yes, but
Mm-hmm.
here, what I'm saying here, like the solvability is for arbitrarily large deformations. And this is a highly
Okay,
nonlinear process.
that
So
sounds like it.
actually, there has been work by, if you know Vasudev Shyam in PI, and I think Mazank, they have shown that you can express, instead of a Taylor expansion as you're suggesting, they have shown that you can express these deformations as a kernel of some sort.
Okay. Okay.
So that would be the corresponding way of describing it.
Okay. One more quick question, which
Yes.
I do not know. If you start with a CFT and you deform it infinitesimally, you need not be still in a CFT, right? You need not obtain a CFT, no?
I don't think so.
Yeah. Okay. Okay. Good. Thanks.
But you get a deformed QFT, but
okay.
Which is one of the reasons. I mean, if that works, then it's really nice. But it is one of the reasons why it's hard to iterate the process on a CFT, because you go from a CFT to a QFT, and then you can't make the same assumptions as you started with. Now, yes, so you can get, because these deformations are solvable, if you know data from the seed QFT, you can get exact data for the deformed QFT. In particular, you can get the scattering matrix. And you can see that if you're considering the final theory, the S matrix of the lambda deformed theory is just going to be related to the S matrix of the initial theory by some multiplicative factor that looks like e to the I lambda, I'm going to say epsilon mu p nu for the scattering of two particles. If you have more particles, just add terms, where this is going to be called a CDD factor for, I believe, Castillejo, Dyson, Dalitz. And is alternatively going to be called gravitational dressing, which doesn't come out of nowhere. The first reason why it can be called that is that to establish this equation, we go to a gravity framework, and we actually get a gravitational dressing. And the other reason why it's logical is that when you deform a theory that is initially local, the TT bar deformations is often non-local. So you get a non-local theory, just like theories of gravity, hence also that name. But again, so if you have the seed QFT, then a very easy multiplication by a single factor gives you the scattering matrix of the deformed QFT. So that's really nice. Similarly, if you have, like for the deformed Lagrangian, well, you know it because we talked about it. You just have this differential equation del lambda L lambda is plus or minus determinant of T lambda. And then you can just solve this differential equation. It's not always easy. It often requires ansatzes to actually get through the calculations, but it usually has a nice analytic expression. I'm going to try to give an example later of this if I have time, which I doubt more and more. You can also access the finite, like the spectrum of the theory at finite volume. So for this, I also have a slide about that a little later, but essentially what we can see is that the energy levels of the new theory follow some fluid dynamics-like equation. Which is called Berger's inviscid equation. And like many, and not all, fluid dynamics equations, because a lot of people are interested in there, like we know how to solve that. The way to do it is, I believe, using the method of characteristics. And so you can get, again, an analytic expression of the new energy levels as a function of the old energy levels. If you're interested, I kind of summed it up here. Please don't read all the lines. That's not really the point. The only things I want to say about that is it all comes from a factorization formula by Zamolodchikov in 2004, so like 13 years prior to the appearance of TT bar deformations. that essentially says that the expectation of the TT bar operator is the the expectation of the product is the product of the expectations, which is really nice. And then just rewriting everything and using the differential equation for the Lagrangian that I showed you and implementing that for energy levels, you just get the Berger's equation, which if you implement it for a CFT seed, gives you something quite nice that you find at the bottom of the page. Now, the interesting thing in there is that you can see that the energy level, the new energy level, curly E, as a function of the old energy level, not curly E, contains a square root. And at some point of the square root, you find a term in lambda. Now, if this term gets big enough in the negatives, the square root is complex. And you break unitarity. So this part of the TT bar deformation is not quite well understood yet. And I think some people are working on that. And this is kind of interesting because that's also the part that gives rise to, like, for, of course, energy levels that are not complex. That's the part that gives rise to a lot of parallels with gravity, between TT bar deformations and gravity. So this is an interesting part to investigate. But anyway, so that's just to give you an idea of what these calculations can look like. And the last thing I wanted to talk about quickly is the fact that you can get also the partition function of the deformed theory as a function of the partition function of the non-deformed theory. And this is going to be given by a differential equation, yet again. The evolution of the partition function is essentially going to look like the partial derivative according to two lengths of the partition function. Because I'm evaluating it on a torus, it has two characteristic lengths. And this is essentially the lengths that are going to matter in the diffusion-like equation that we get. So many different point of view, many different quantities, but always some rather easy equation to describe them. Now that tells us why these deformations are nice to study. And I want to give a concrete example of one of them, just for you to have an idea of what TT bar deformations look like in general. If you take a Lagrangian, the most simple one that you know, which is like the Lagrangian, the complex scalar here, if you actually carry out the whole like solving the differential equation for the Lagrangian bit, you will get that the deformed Lagrangian looks like some constant, depending on the deformation parameter, plus the Nambu-Goto Lagrangian of the string. Illustrating what I said earlier, which is that if you start from the theory of a point particle, TT bar deform it, you get a theory of a string that is highly non-local. Of course, what you think works, works. When you take the tension of the string to infinity, the string shrinks to a single point particle, and you recover the lambda equals 0 non-deformed theory. You can also check that to first order, you get indeed a deformation by lambda TT bar. I don't want to spend time on this. I already spent enough time on that part. So these deformations seem to be highly studyable. We know a lot of things about them. We know a lot of things about the deformed quantum field theory. Now, that does not tell us why we want to study them, because it's not because we have access to this information that we actually really want this information.
Can I ask a little question?
Yes.
Maybe at the end you can answer if you don't want to answer now. Up
Sure.
there you had 1 over lambda plus or minus 1 over
Yes.
2 lambda plus Nambu-Goto action. So when you were saying, when we were talking about the theory, I was thinking like this: the QFT, initial QFT is lambda equals 0. But
Yes.
here, when you said you can't just take the limit lambda goes to 0, right?
No, you can. You can. There's
because of factors in Nambu-Goto somehow?
Yeah, there's
Like,
going to be a 1 over 2 lambda in Nambu-Goto.
okay, good. Thanks. All right.
Yeah.
Oh, yeah. Of course, that is the. Yeah, I forgot that part. Thank you.
No, you can take that limit, and the whole point is that limit actually works. That limit gives you what you're supposed to get.
Yes. Okay.
So yeah, the take-home message of this is TT bar are unique kind of irrelevant deformations because they're not just irrelevant, they're solvable. So we like it. However, it's not because we can solve them that we want to solve them. And the motivations behind why we care about these theories is their strong relation to gravity. They are intertwined with gravity in many different ways. The first way was proposed by Carty, I think 2018. And it was argued that an infinitesimal, this time, TT bar deformation, can actually be related to coupling the theory to a random geometry and integrating over random geometries in a path integral way. Now, what do I mean by that? Well, if I want a deformed action, like TT bar deformed action, the infinitesimal deformation is going to look like exponential of del S lambda, is going to look like exponential of del lambda over 2, integral of TT bar, determinant of the stress tensor. So the determinant can be written as a product of epsilons times a product of t's. I'm not going to enter indices here. Well, this, by some clever Herbert-Stratanovich trick, because it looks like a quadratic in there, can be rewritten as some Gaussian integral involving a new variable h, which, as you probably guess, is going to be the random geometry, the random metric. And you can rewrite this just as e to the -1 over 2 delta lambda times integral of epsilon epsilon hh. So the determinant of the metric, the new random geometry, plus integral of hij tij. Now, by definition of the stress tensor, this is essentially telling us, oh, the new metric has now, like, it was the old metric, say delta ij, plus this hij. And this term here is easily computable with saddle point approximation because that parameter is infinitely small. And so with that, we just get a reinterpretation of a TT bar deformation as just coupling to random geometry, integrating over the random geometry. The nice thing is, on top of that, you can actually consider the random geometries flat. I'm not going to explain why, but so you can only integrate over flat random geometries. This, in particular, will give you, if you carry out all the calculations, that the deformation, the evolution of the partition function along the flow is going to look like 1 over 2 times, if you compute it on the torus, sorry. So if you look at a torus, that is going to look like, well, L2, L1, essentially. The evolution of the partition function is just going to look like 1 over 2 times the area of the torus, some epsilons, and then some derivatives with respect to the metric times the partition function. These derivatives really only depend on some parameters defining the metric, which in turn are the moduli of the torus. So this is how you can establish this differential equation on the partition function.
Can I ask some questions?
Sure.
Is this flat summing over flat geometries related to conformal arguments? One, because you're doing 2D models. This is a 2D model deformation, no?
Yeah, it is 2D. I don't remember, probably.
Oh, okay, we can discuss that later.
Yeah, we should discuss that later. But my main point here is to just give some ideas of like why TT bar deformations give fun stuff. Okay, but I don't remember all the steps. Yes.
No worries. The second one is this, you said moduli of tori.
Yes.
Can you literally count all of them with the correct multiplicity, so to say, using these? Because when you look at the moduli space of tori, there are some points in the moduli space which have whose stabilizers are not the same, right? So the actual space is an orbifold, not a I mean, like it's a weird space, the modular space. I couldn't explain it well, but is this correct?
Yeah, I think so. I mean, essentially, all this is supposed to tell you is that you're just going to have derivative with respect to the metric. Now, the metric on the torus is actually just going to depend on some parameters.
Sure.
And like these parameters can all be related to the real and complex, real and imaginary parts of the two generators of the torus.
Okay.
That's what it is. And actually, here I'm saying this. When I write del L1, del L2, I'm being very schematic, and it's actually just like two derivatives with real imaginary part minus two other derivatives with other real imaginary parts.
Okay. All right.
All right. So that was the first perspective. You're very welcome. The second perspective is this time not only for infinitesimal TT bar deformations, but for arbitrarily large TT bar deformations. And it's been proven this time by Dubovsky, Gorbenko, and Mir-Babai that, Dubovsky, Gorbenko, and Mir-Babai, that TT bar deforming a QFT can actually correspond to coupling it to two-dimensional flat space JT gravity. In other words, if you want a TT bar deformed action, that I'm going to call S lambda, it's going to correspond on the gravity side to an action S capital lambda, where this is just cosmological constant, which is going to be the action of your initial QFT in some space with some metric, plus the JT gravity term, integral of square root of minus g, phi times r minus lambda, where here, the deformation parameter small lambda corresponds in the gravity world to -2 over lambda, the cosmological constant. And this picture is what allows you to derive the equation on like the CDD factor equation, where you say that S lambda is going to be CDD factor times S0. With that perspective, if you actually compute the action of the deformed theory and the action of the initial theory, you can relate them with the gravitational dressing we talked earlier about. And finally, I want to give a third perspective really quickly, because I'm extending my welcome a bit here. But this is an interesting one, so I don't want to skip over it. We know that we can define TT bar deformations on two-dimensional QFTs. In particular, they can also be defined on two-dimensional CFTs. And for gravity people, I'm not such a person, but for gravity people, two-dimensional CFT kind of rhymes with three-dimensional ADS. And the idea is this is going to correspond to an ADS3 gravity picture, where the fact that we're imposing a deformation, a TT bar deformation, is going to restrict the ADS space to a finite cutoff. So lambda equals 0, no deformation, ADS space, infinite ADS. And then as you deform, you're bringing back the boundary of ADS, and you're imposing a Dirichlet boundary condition on that boundary at finite cutoff, RC. And this is, by the way, only working for what I could call the bad sign of lambda, the sign that gave us complex energy levels earlier in bad conditions. So this is a little odd, but it is what it is. And the deformation parameter lambda, yes, Jem?
When you say bad sign of lambda, what does it make the sign of the gravitational counterpart? Is this the correct sign for Einstein-Hilbert or the vice versa?
Yeah. No, the sign for ADS3 gravity is good. But the point is that the lambda here that we have is going to correspond to -g over RC squared. And so we like, in order to account for all the nice things on the gravity side, we need a negative lambda on the deformation, on the TT bar deformation side. And having a negative lambda on the TT bar deformation side imposes this weird spectrum that we saw earlier with sometimes some complex values.
I mean, incidentally, in the three-dimensional gravity, the solution, BTZ solution, for unitarity, I think in TMG, you need the bad sign for the Einstein-Hilbert term.
Right.
I mean, it's vice versa there. I don't know, just a comment.
Okay. I don't know much about that, but it's, I actually don't even know what, like, yeah, I don't even know what the corresponding things to the complex energy levels will correspond to in, yeah, that's.
I mean, you're considering a larger class of stuff, I mean, models. I'm just giving you a particular instance of where a bad sign appears in a 3D gravitational model. So.
Okay. Yes, thank you. Where was I? Lambda minus G over RC squared. And yeah, so everything that you otherwise think will hold holds. So the deformed stress tensor on the TT bar deformation side corresponds to the boundary stress tensor on the ADS3 space, et cetera, et cetera. And the conservation of the stress tensor is going to give you the Einstein's equation on the other side. So everything works out. So as you can see, there are already like 3 different pictures, 3 different links between TT bar deformations and gravity. And this alone is kind of enough to motivate why we would care about such deformations. Now, our talk, the purpose is to get infinitesimal deformations of 2-dimensional CFTs from 4-dimensional Chern-Simons. So in order to do that, I'm going to need to define 4-dimensional Chern-Simons. And prior to giving it a rigorous definition, I would just like to motivate why we thought about Chern-Simons in the first place in this story. So for those who know a bit about Chern-Simons theories and what's happening around them, if you take a 4-dimensional Chern-Simons and you compactify it on a circle in what will be called the holomorphic direction once I get there, you get 3-dimensional Chern-Simons. And if you further compactify on a circle, in this time the topological direction, you will get something called 2D BF theory. Now it is well known that BF theory is related to 2D JT gravity. And it is also well known that 3-dimensional Chern-Simons theory, if you make some identification of the gauge field in terms of spin connection and Vielbein, gives what I'm going to call 1/2 of 3D gravity. 1/2 because we kind of need 2 copies of it. But then according to what we just saw, 3D gravity through this ADS CFT picture is related to 2-dimensional TT bar deformations. And 2D JT gravity, according to the other correspondence that we saw, is also related to TT bar deformations. So the question kind of is, in this case, can we relate directly 2D TT bar deformations to 4D Chern-Simons? And more importantly, which we have not done yet, which is kind of the future work, does this diagram commute? As in, if we actually take the TT bar deformations on the 4D Chern-Simons side, we go all the way down the scale, can we actually get the same deformations as we would get in using the correspondence with 3D gravity and the correspondence with 2D JT? All right, so 3D Chern-Simons setup. I think it's important to redefine quickly the 3D Chern-Simons before going to 4D. I'm not going to spend too much time on it, but just going to write the action in 3 dimensions. So if you consider a Lie group G, an associated, well, the Lie algebra of that Lie group, small g, you take a connection that you're going to call A, which is going to be a Lie algebra valued 1 form. A manifold, for example, R3, you consider an invariant bilinear form on your Lie algebra. I'm just going to call trace. and you take the Chern-Simons level K, then you can write the three-dimensional Chern-Simons action as K over 4 pi, I think, integral over the manifold of the trace of A wedge dA plus 2/3 of A wedge A wedge A. Now that's your usual Chern-Simons picture, where you call this whole thing the Chern-Simons 3 form, CS of A. This action has a gauge symmetry, which is just given by A goes to A plus dA xi, where xi is just a C infinity function on the manifold, and dA xi is just d xi plus the commutator of A xi. Now, if you want to go to 4 dimensions, and that was a trick that was introduced by Kevin Costello a while ago, the main idea, I should have said that this action here, I wrote it, but I didn't say it, that this action is a topological action. So it's topological in 3 directions because you don't see the metric appearing there anywhere. If you want to go to 4 dimensions, the idea is that you're going to partition the 3 dimensions. You're going to keep, if I take the example of R3, you're going to keep the first 2 directions, X and Y. And you're just going to keep them as 2 topological directions. And you're going to call them W bar for convenience, with W a complex variable. But this is not really something where we demand a complex structure. It's just to rewrite R squared as C. But then you're going to take the 3rd direction, which was initially real, and you're going to complexify that direction to make it the holomorphic part of a complex variable, Z and Z bar, where this time we require that we have a real complex structure on this, like an actual complex structure. Now, the more general picture of this is to get a 4-dimensional manifold on which you can define Chern-Simons. You need a 2-dimensional oriented surface, which is the one that I parameterized with W. And you need a complex manifold that is endowed with a meromorphic 1 form that I'm going to call omega. And the role of this 1 form is essentially to complete the Chern-Simons 3 form and make it a 4 form. So the way you can define the 4-dimensional action is just by saying, okay, well, I keep the K over 4 pi. And now I'm integrating over my 4-dimensional manifold. I already have a Chern-Simons 3 form. So I can just write it here. But then I'm going to wedge this with my meromorphic 1 form, omega. Now, this can seem a little abstruse, but in practice, this is rather easy to see, because a good example of this meromorphic 1 form is just dz. So essentially, it's as if you had like z bar, w bar as your 3 real directions of your 3D Chern-Simons, and then you wedge with dz to give a 4th direction. For this talk in practice, we're going to take as well the complex manifold to be just C. And we are going to take G to be SL2C. Yes, there was a question.
I will ask at the very end. Yeah, I've asked so much. I will not stop.
I will try to, well, I can't end on time, obviously, but I will try to end as much on time as possible. Now, the idea is that this 4-dimensional Chern-Simons theory still has the same gauge symmetry as before, because we've basically not touched the Chern-Simons 3 form. So we still have this A goes to A plus D xi. But we also have an extra gauge symmetry, which is the Z component of A goes to anything, AZ plus any function. Why? If we have a DZ wedge in our action, all the z components in the Chern-Simons 3 form are going to be completely irrelevant because it's wedged with dz. So really az can be anything. And so we have this further gauge symmetry. Now you can fix this gauge symmetry by just requiring that az be 0. And you can fix the other gauge symmetry. I'm going to skip over the details, but essentially by requiring that az bar equals 0. This is just some holomorphic gauge fixing. And then what you're left with is a new 4-dimensional Chern-Simons gauge field that actually looks like a 2-dimensional Chern-Simons gauge field that only has W and W bar components. And your new 4-dimensional action is going to look like k over 4 pi integral of the manifold of the trace of AW dz bar AW bar dv. So you are in 4 dimensions, but you're effectively keeping only 2 of your gauge fields, of the components of your gauge field. Now, the essential question is, why do we care and why do we need this? Like, why does this help at all get some like 2-dimensional TT bar deformations? Well, this comes from the fact that because our action now looks like this, there is only one propagator in this action. It's a propagator between the W and the W bar components of A. This propagator looks something like the Casimir of the gauge group, divided by 2I pi z minus z prime, delta of W minus W prime. This doesn't seem to matter yet, but really the idea is that we can pair AW and AW prime. That's all you need to know. Now, in this 4-dimensional theory, assume that we insert 2 planes, one at some value of z, z0, one at some other value of z, z1. And assume that we have a theory on these 2 planes. We don't say which theory yet. And this theory has a current, and we manage to couple on one of them the W bar component of A with some holomorphic current, and on the bottom one, the W component of A with some anti-holomorphic current. Well, because there is an AJ vertex and an AJ bar vertex, and because A and A bar are coupled by a propagator, what you get from the interaction is just a term that will look like, I'm being on purpose very non-rigorous here because it doesn't matter to have the details, but you're going to get a term that looks like JJ bar because you're going to have a propagator between AJ and AW bar, well, AW bar J and AWJ bar. This propagator is just going to give you, in the world of effective field theories, a JJ bar interaction. Now, what we want is not just any JJ bar interaction, we want TT bar interaction. But that's close enough. So really, when we said that we wanted to put a theory on the plane, what we're going to want to do is take the conformal field theory that we want to deform, the 2D CFT we want to deform, make sure that it can be split into chiral and anti-chiral sectors. And if so, put the chiral sector at Z1 on the plane of Z1, put the anti-chiral sector on the plane at Z0, and couple each of these sectors through the stress tensor, so through the holomorphic stress tensor or the anti-holomorphic stress tensor, to the components of the gauge field. And if you do that, then the J that we had here is really a T now, and the J bar that we had here is really a T bar. And if you compute the 2D effective action by integrating out the gauge field, you're just going to get some TT bar deformation. Now, the actual way of doing it, and I'm going to completely gloss over it, you can read it if you really want, is slightly more complicated than that because we have to respect symmetries. we have to respect the fact that there's an SL2 here, gauge group. And so the currents that we introduce cannot quite be just the stress tensor. They need to be the stress tensor dressed with some clever powers of the holomorphic and anti-holomorphic variables so that they satisfy some commutation relations. It's not really important. The point is you can define some currents. You can couple them the way I said. And in the end, you will get integral of square root of minus g tt bar divided by 2i pi z0 minus z1. And in this picture, this square root of minus g here is going to come from the extra powers of the holomorphic and anti-holomorphic variables that you needed to define the currents. This tt bar comes from coupling a bar to t, a to t bar, and making them interact through a propagator. And this 1 over 2 I pi z0 minus z1 is just your lambda, your infinitesimal parameter. And you can tune it. You can make z0 and z1 as close or as far away as you want. In particular, you can make this 1 over 2 I pi z0 minus z1 infinitesimal. And then you have the exact definition of a TT bar deformation, which is the initial action of your CFT plus lambda, 1 over 2 I pi z0 minus z1, square root of minus g TT bar. One thing I should address is the fact that you don't really have the choice of the powers of the holomorphic and anti-holomorphic variables that you're using to define the currents to which you couple. And so this coefficient here that you get, I call it very nicely square root of minus g, but really it's just a polynomial, like a quotient of polynomials of w, like of the holomorphic variable. And it doesn't really have to be a metric. If it's not a metric, you don't really get anything. But if you can recognize a metric, then you manage to actually say, well, this is a TT bar deformation on a space that has that metric. In the example that I took, the metric that you get is dw bar over 1 plus norm of w squared, the whole thing squared. And that's just the CP1 metric. So with the gauge group that I chose, with the meromorphic one form in the 4D Chern-Simons theory that I chose, then we just get TT bar deformations on CP1 of a two-dimensional conformal field theory that is on CP1. With different choices, you will get different square root of minus g's, which will correspond to a TT bar deformation of a CFT on a different curved space. We could get like ADS space with that. We could get the cigar, like a space endowed with the cigar metric, various geometries. And so really, what you can do is actually play on the values of, well, play on the gauge group and play on the meromorphic one form. And by tuning these, you can tune the geometry of the space on which you're actually performing a TT bar deformation. Now I'm getting to the end. What we have shown in this is that if you take a 4-dimensional Chern-Simons, you take the 2-dimensional conformal field theory you want to deform, you put its chiral part on a plane, its anti-chiral part on another plane, you couple to Chern-Simons, you integrate out the Chern-Simons gauge field. Then provided you made good choices in your life, you get a TT bar deformation on curved space with some metric. And if you tune the parameters that you chose, you can tune the geometry of the space on which you're TT bar deforming. Now, what we would like to do, and haven't done yet, is extend this to non-infinitesimal TT bar deformations. Because right now we made use of the fact that we just need to do plus lambda TT bar. The actual deformation is a little more complicated than that. And we don't know how to generalize it yet. And the other thing we would like to do is relate it to the other correspondences between TT bar and gravity, as I talked about earlier. And I think I can stop here. Thank you all for your attention.
Thank you, Victor, for this nice talk. So do you have any questions from the audience? I have one.
Okay, go ahead.
Just a small question. You identify the lambda with 1 over the difference of z.
Yes.
It feels weird to have a small lambda for a distant, really distant z's. Does it imply something physically? Does it mean anything like when the lambda is small, the planes should be really far away?
It does kind of mean something. Like if you consider, so essentially, the fact that you're putting what you're doing could be very artificial. Putting the chiral sector on a plane, putting the anti-chiral sector on a plane, and then by integrating out the gauge field, what you're really effectively doing is merging the planes. So if you didn't have any interactions, you would just put the chiral and anti-chiral sectors on 2 planes, merge the planes, recover the initial QFT. Easy. Now you're introducing interactions through the fact that the 2 different components of the 4-dimensional gauge field, what I called AW and AW bar, have a propagator, have a non-trivial propagator. And this propagator is all the stronger, like its magnitude is all the bigger than the planes are close together.
Yeah.
So intuitively, if you take the planes super far away, then it's as if you had almost no coupling between these planes.
Yeah.
And when you integrate out the gauge field, you almost did not disturb the initial theory. If you take the planes to be very close, then you have a very strong coupling, and then you actually deform the theory a lot. But that's not what we want to do, because if you deform a lot, you're not just allowed to deform by lambda TT bar. You need to go through this whole differential equation process.
I see. Thank you.
Does this answer your question?
Yeah, thank you.
Cool. Thank you.
Other questions?
I can ask one. Sorry, I couldn't turn on my mic. So I have a question about the formulation of the 4D Chern-Simons action that you were considering. So in the usual 3D Chern-Simons, as you have stated, your data is just a principal bundle with a connection over a 3-manifold.
Yes.
Now here, you give me a 4-manifold in the form of a 2 product of one 2D real manifold and a complexified one-dimensional complex manifold, no?
Yes.
Yeah. And you put in an A eventually.
Yes.
Where does this A live on? What is the definition of A here? You're doing a sleight of hand here, I think, a generalization of something, but I wanted to ask.
Rigorously, like
Yeah.
if you want the like connection on some principal G bundle story for the 4-dimensional Chern-Simons, I couldn't tell you right now. I would have to actually like read the paper by Costello more attentively.
Mm-hmm.
When I wrote this, my point was not quite to rederive the whole thing. I could just kind of try and dodge the question by saying, really what we're considering is a Lie algebra valued 1 form.
On which one, in this case? For instance, in your particular example,
yes.
Where does A live on? It has just DW and DW bar part, no?
No. It has all the parts. It has all the parts.
Then you gauge fix them. Sorry. Then you gauge fix them. Sorry.
Yeah.
Okay.
So it is just literally a Lie algebra valued 1 form with a DZ component, a DZ bar component, a DW component, a DW bar component. Now, where DZ is the specialized direction, it's the weird direction in which you have a DZ wedge in the action that is modifying the whole behavior of the story. And then what you're doing is using the DZ wedge in the action to gauge fix AZ to be 0. And then you're using the rest of your gauge freedom that comes from the 3D Chern-Simons gauge freedom to choose AZ bar to be 0.
Yeah, thank you.
And then effectively you have a 2-dimensional gauge field, but truly you have a 4-dimensional gauge field. Like your gauge field is written like that over all components.
Okay. So when you were solving your particular example, the reason that you chose G to be that,
yes,
it had motivations from ADS, no?
No. Well, it can probably have some if I knew ADS better.
You can write it in terms of two SL2Rs.
Yes. Yeah.
You need some Lorentzian metric, hopefully. I think that's one of the worries for a physical application. So I think SL2C is a good way to go to begin with anyways, right? For ADS3 is there.
Yes, it can certainly have an ADS motivation. The motivation, like the side of the motivation that I was seeing was that if you, it all comes from gauge, to keeping the gauge symmetry in the action with the couplings. You can't couple to anything because of the SL2 gauge symmetry. Well, because of the gauge symmetry. And the idea is, because you're looking to couple with the stress tensor,
oh,
and because you're going to have, what?
Is it trace-free because you're working with SL? Can you claim that? No, please, you answer. I don't want to turn this into a discussion. My bad.
No, because you're coupling just A with the A's with the T's, so to speak. And because the A's are going to transform according to, you know, the adjoint representation of SL2, you kind of need the T's to transform oppositely.
Oh, okay. For it to be invariant.
Exactly, for it to be invariant. So you want the T's to mimic an SL2 algebra. Well, you want the T's to mimic the Lie algebra that you're choosing. And what you know is that you can very easily get Virasoro with the stress tensor of a 2D CFT.
And you computed us as some sort of a central charge now, which was the Casimir. It looked like a central.
The Casimir is there just because you will have a propagator between E and F, a propagator like if you take the SL2, you have EF and H, you're going to have a propagator between E and F, between F and E, and between H and H, yes. And so the full-on propagator that is not color stripped is the Casimir, like the second Casimir.
That makes sense. Yes. Again, invariance arguments can work here.
And yeah, but like the part that you're asking about is really what took the longest in this paper by very far, like figuring out a way of making the coupling invariant under gauge transformations. And for this, we needed the T's to replicate the Lie algebra. And so there is only a small number of choices that you can have for your Lie algebra because you can't make the T's imitate any Lie algebra. You can do SL2, you can do the isometries of the plane, you can do a few things like this, but I don't know how many other you can actually do. So this is a big limitation on actually how many geometries we can recover.
I mean, one more comment. Have you checked some sort of like Sugawara type constructions where these T-minus come from some sort of current algebras and their generalizations to infinite dimensions, Kac-Moody type?
That would be one of the future work thing that I would need to do. Not yet.
Okay. All right. Thank you for this talk, by the way, and thanks for staying so late for us for the both of the days.
Victor, thank you for this nice talk. And with this talk, actually, we are concluding our event. This was our last talk for this year. And I would like to thank you for everyone, first of all, our speakers and then our attendees who listened to these talks. So I hope you enjoyed during these 2 days. I had very nice talks to see. Like I usually don't have chance to see this kind of diverse topics in the same place. So this is a really nice chance for all of us. And also we are seeing all these talks in the introductory level. So this actually opens the door for the new people in the area too. So I would like to thank again to my friends from the organization committee and everyone attended in this 2 days. So, and with this, I think we are concluding our event. So if you can open your cameras, maybe we can take a last event photo before leaving.
We already do that. We already did that.
Okay, thank you everyone for attending again and see you next year. Bye-bye.
Okay, thank you. Bye-bye.
Thank you, everyone.
Thank you so much.